So I'm speaking on how to capitalize on machine learning. So in 20 seconds, here's why machine learning is important. Business needs prediction. Prediction requires machine learning, and machine learning depends on data. So putting that reverse, we have data, we give it to machine learning. It generates models that predict, and we use those predictions to improve pretty much all the main large-scale operations that we conduct as organizations. So for that reason, we also refer to these types of predictive enterprise use cases of machine learning as predictive analytics or also predictive AI. And that way we boost sales, cut costs, combat risk, prevent fraud, fortify healthcare, streamline manufacturing, conquer spam, and win elections. As Morgan Vaughter put it in the foreword of my new book, The AI Playbook, machine learning's practical deployment represents the forefront of human progress, improving operations with science. So in a nutshell, predictive modeling, the core machine learning algorithm, the thing that learns from data, does that number crunching over the training data, the historical or labeled cases of data from which to learn, and generates what I depict as a golden egg in these slides. That's the thing that does the predicting. That's the thing that we've learned. That's the thing that is then used in deployment to improve all these large-scale operations in marketing, sales, fraud detection, etc. The problem is that all too often, these projects actually fail to deploy. So although the first part works, the number crunching, we get the predictive model, it doesn't actually get integrated, operationalized. Operations aren't actually changed with them. And that deployment piece is a big deal. That's the only way you actually realize or capture value from the model. As a result, as IBM industry research recently showed, the average returns on AI projects is lower than the cost of capital. And in surveys of data scientists that I was involved with, it turns out data scientists say the same thing as the executives. They develop a predictive model with the intention that it be deployed. Stakeholders get cold feet or something goes wrong, and you actually fail to achieve that actual deployment. Only 22% of data scientists say their new initiatives usually deploy. That is more than 80%. So the problem is, this is all a symptom of, I believe, a major unmet need in the machine learning industry, which is that there's no standardized, established business paradigm practice playbook for running machine learning projects successfully end-to-end through to deployment that's well known to business stakeholders. In fact, most business stakeholders don't even recognize that you really do indeed need a very particular specialized business practice in order to successfully run machine learning projects. And hand in hand with that, we have this other unmet need, which is that business stakeholders, anybody involved with making decisions about or touched by the machine learning project and its potential deployment, needs to ramp up on a certain semi-technical, very accessible, interesting, but often unknown amount of know-how, background, knowledge, semi-technical, let's call it data literacy, needed by the business stakeholders so that they can then, in an informed way, collaborate deeply across the project. And that's probably the bigger point of the two if I had to choose one. Now, as you'll see by the end of these slides, both sides, if you will, the technical and biz, the data scientists and their client stakeholders, are both kind of pointing to the other party to say, hey, you're the one who should be taking this up and making sure that there's deep collaboration involved in semi-technical details around the project and ensuring that the project is run from a business standpoint, but with details related to what machine learning is going to do. Everyone's like, it's not my job. So that's the problem that I'm here to try to solve. I'm going to get a little more detailed about defining machine learning predictive analytics, and then we'll address the problem, why machine learning projects routinely fail to deploy. And then the green is the solution, that semi-technical understanding, the particular know-how that all business stakeholders could, should, and would understand. Fascinating stuff. And then the BizML paradigm, that 6-step playbook that's also covered by my new book, The AI Playbook. So I'm the author of this earlier book. I'm the author of 2 books. This is Predictive Analytics, which was the first accessible, concrete, somewhat detailed book covering machine learning, but accessible to any reader. It's been adopted at hundreds of universities as a textbook, but it doesn't read like a textbook. It's very much kind of pop science, anecdotally driven, accessible, understandable, lots of case studies, and is a bestseller. My new book, which just came out last week, second book, is the AI Playbook. If the first book is sort of how machine learning works, how it operates and delivers value, this is how to use it, how to capitalize on machine learning. So the title of the book is the AI Playbook, Mastering the Rare Art of Machine Learning Deployment. And that's the content I'm covering today. I'm going to tell you as much as I can about what's in the book over the next 20-25 minutes. I'm also the founder of the long-running Machine Learning Week conference series, previously Predictive Analytics World. We've been running it since 2009. This year in the US, it'll be the first week of June in Phoenix, Arizona, and in Europe, it'll be in November in Munich. You can find out more at machinelearningweek.com, and we've launched a new co-located sister event first week of June in Phoenix, Generative AI World. I'm also the executive editor of Machine Learning Times. It's a news portal, and you can get the monthly email newsletter for free, machinelearningtimes.com. I'm the instructor of this course, Machine Learning Leadership and Practice End-to-End Mastery, which basically covers the contents of both my books, plus a bit more on the technical side, but in an accessible way. Find out more about that at machinelearning.courses. All right, let's define machine learning in a concrete, practical way. So we're going to turn to this book. This is a real book, Machine Learning for Babies and Toddlers. That's a picture of me reading it to my son a couple years ago. I recommend this book for babies, but not so much for toddlers. I didn't like the definition. Let's turn to this really applied, practical definition. It's technology that learns from experience. Now, by experience, I mean data. Data is a recording of prior events. It encodes the collective experience of an organization from which it's possible to learn. And what do you want to learn? You want to learn how to predict. Prediction is the holy grail for driving operational decisions. Large-scale operations conduct of lots of decisions: who to contact for marketing, investigate for fraud, where to drill for oil, which satellite to investigate is potentially running out of battery. That's what it all comes down to. Prediction is the most actionable form of analytics because the predictions for each individual that it provides directly informs the action to be taken with that individual. So when I say individual, I'm going to be talking about humans like customers or healthcare patients. I could also be talking about corporate clients, other companies. I could be talking about which wheel of a rail of a train is going to have a fault. It's at that level of detail, somehow an organizational unit. That differentiates it from forecasting, right? So forecasting is the economy going to go up or down next quarter? How many ice cream cones are we going to sell? This is, what are the chances this one particular customer is going to buy an ice cream cone? So it's on that per individual level, which directly informs decisions to be taken with that individual. That's why it's so actionable. That's why machine learning is hot when it comes to enterprise practices. So it predicts the outcome or behavior for each customer, patient, business, vehicle, image, piece of equipment, or other individual unit. We're not done yet. In order to drive better decisions, that's key. If you don't actually apply what you've learned, make the predictions and act on them, integrate it, operationalize it, deploy it, these all mean the same thing, and that's often the missing part, then you're not capturing value. The number crunching alone is not intrinsically valuable. It's literally useless if you're not using it to actually change and thereby improve operations. So in a nutshell, the data comes in from the left, and this core method, machine learning algorithms, predictive modeling algorithms, same thing, does the number crunching. It learns from those historical cases and produces the predictive model, whose job is now to make those predictions. So now in deployment, when we're actually using it after it's been trained, after it's been developed over data, is now we give it one individual at a time, the characteristics known about that one individual. And then it takes that as input, that's what it's been trained to do, and produces a probability, that's a prediction, as to whether that individual will click, buy, lie, or die, whatever outcome or behavior we're trying to predict for each individual for this particular machine learning project. Now we're going to act on the score. So that score is a probability. This is essentially the creation of a probability calculator. To predict is to put a probability on something, unless you want to be absolute. This person's definitely going to win the election. This individual customer is definitely going to make a purchase. But there's no reason to make a definite. We don't have clairvoyance. We can't expect computers to either. They predict better than guessing. That's the value. So the more innuendoed, meaningful, and useful thing is to put a number on it, a number between 0 and 1, or between 0 and 100, same difference, same thing. That's an American expression, same difference, but same thing. And that's the likelihood, the chances that you'll see that particular outcome for that individual. If it's a 50-50, if it's a 50%, you're like, I don't know. That's the definition of uncertainty. If it's 99%, you're pretty confident, right? If it's 1%, you're also pretty confident that it's not going to happen. Now, this pertains both to literally predicting an outcome or behavior in the future, what's going to happen, and also for detection or diagnosis. Is this transaction fraudulent? Does this healthcare patient have a diagnosis? Should they be given a positive diagnosis? Right? And what's the probability of that? That's not literally what's going to happen in the future. It's not prediction of the future. But either way, you're trying to ascertain an unknown, put probabilities on that unknown. So we do use the word probability. We do use the word predict for predict whether this transaction is fraudulent. Either way, it's a predictive model. That's the terminology. So that's the rub. That's the problem. That's part of the dilemma here, is that in general, outside us nerdy quants, us data scientists, people often are kind of uninterested in probabilities. They think it's too technical. It's a simple concept. For example, turn to Empire Strikes Back. You've got the very helpful, intelligent robot, C-3PO. Sir, the chances of us successfully navigating this asteroid field are 3,221 to 1. And then our beloved hero, everybody's favorite hero, says, never tell me the odds. And I'm like, thanks, George Lucas, for reaffirming to the world that we should ignore probabilities. Whereas probabilities are what it means to apply science to data and learn from it and maybe make better decisions, right? So I love Empire Strikes Back. Just saying, right? Now let's turn to something maybe not quite as popular, but Moneyball, both movie and a book, where the Oakland A's baseball team ended up doing a lot better than anyone expected, given limited resources, because they actually did deploy analytics and they made discoveries and drove decisions about which player to put up on bat, etc., based on those analytics, and it really, really paid off over time across games. This movie celebrates that rare union between the business stakeholder and the quant, the data scientist, between the beauty and the geek, right? Can you guess which actor played the data scientist in this movie? But Moneyball is the epitome of glossing over the math. So we got to get involved with a little bit of details. Now, getting more detail, we got Nate Silver's very famous best-selling book, Signal and the Noise, about probabilities, and he espouses probabilistic thinking. But a lot of data scientists would be disappointed to recognize that although probabilistic thinking may now be in the zeitgeist popularly, what's not in the zeitgeist is probabilistic doing. That is to say, systematically acting, not just on one-off predictions like whether the economy is going to go up or down or whether there's going to be an earthquake. That's the kind of things that Nate Silver covers in this book, but rather routinely and systematically operating on probabilities over and over again for hundreds of thousands or millions of decisions of who to contact, which transaction to audit for fraud, where to drill for oil, all those large-scale decisions where there's lots of decisions, and you're systematically applying probability over many decisions. I call that probabilistic doing, and that's the thing we need to get into the zeitgeist. Similarly, Nate Silver was kind of ostracized and unfairly, I would say, for his model at the end of the 2016 U.S. presidential election, saying there's a 71% chance that Hillary Clinton's going to win versus 29% for Trump. Trump did win. Does that mean his model was bad? No. Now, a lot of other models had really high confidence. They put 99 or even higher, 99.8% or whatever, that Clinton was going to win. You could say those perhaps were overconfident. But this result of a 29% chance of Trump winning, that is not a long shot. Something that happens 3 out of 10 times should not be a surprise when it happens. That's what a probability is. So to the degree that people say, hey, this was the death of data, poll data is invaluable. No, the takeaway from saying 70% or 71% is more shrugging your shoulders, uncertainty, because that's closer to 50% than it is to 100%. It's closer to a complete toss-up, I don't know, than it is to absolute certainty and high confidence that Clinton was going to win. So we need to learn to understand probabilities correctly. If not, we're not applying science to business. And in particular, for machine learning, it comes down to 3 semi-technical but super accessible concepts. For each project, you got to get involved with and understand 3 things. What's predicted, how well, and what's done about it. So I'll go through a bunch of examples and then show how those relate to the 6-step practice, the project paradigm framework that I call BizML. It kind of corresponds to 3 out of the 6 steps. Now, these 3 to data scientists are known technically as the dependent variable, that's what's being predicted by the model, metrics, which is measuring how good the model is, how well it performs, and deployment, that is the integration, operationalization, going to production, actually acting on these predictions and changing operations accordingly. So for example, one of the main 2 marketing applications of machine learning is response modeling, where what's predicted is, will this individual customer buy if contacted? That's a pretty specific yes/no question. You put a probability on that, and then you use that probability to decide what's done about it. Well, mail a brochure to those above a certain threshold, those likely to buy. It's quite straightforward. So in the deployment, you're looking at a customer today, you're saying, hey, should I expend the cost of contact? Should I spend $2 sending a glossy brochure to this customer? If I do, what are the chances there'll be a positive outcome in the future? They'll respond in the sense of, because of in light of seeing that brochure, will they buy the product? Now, let's jump straight into the metrics of why this pans out from a business value standpoint. If I took all of my customers and I had a model and it could predict the chances they would buy if contacted, and then I sort the list, I order it from the top, most likely to buy, down to least likely, that is and then order it from left to right. So as I go through this chart from left to right, I'm going down the list from most likely purchasers down to least likely if contacted. The top curve is called a profit curve, corresponding to the campaign. And as I first contact those customers most likely to buy, as predicted by the model, my profits increasing at a sharper rate because I'm getting a better bang for my marketing buck. I'm getting a higher proportion of actual responses for all the spend I'm doing. Now, after a certain point, around 24%, I've kind of exhausted those higher echelons of more responsive customers. And now the marketing stops paying off. And in fact, if I keep going down the list, I only lose money because I'm not getting enough bang for my marketing buck. To the point where ultimately on the far right, I will have lost $550,000. That is to say, this is not a profitable marketing campaign if I did mass marketing and didn't target at all predictively. If I just contacted everybody, it wouldn't matter what order I contacted them in. The math would tell me I'd get a negative $550,000 profit. That is a loss, of course. And that lower straight line is the baseline. If I had no model and no particular basis for ordering or prioritizing customers, and I essentially were just contacting them in a random order, then the more I contact, the more on average I would lose. And either whatever order I contact them, on the far right, by the time I've contacted everybody, I will have lost the same amount of money. Now, this type of view is actually really rare. It's strange. If you're outside of the field, you might think, well, duh, no brainer. Let's look at profit. Let's look at a profit curve. But no, actually, the way these projects are, one of the main reasons they're failing is that they tend to stop after a technical metric. And I'll talk more about those, but just sort of the relative pure predictive performance, not the business metric, the KPI like profit in this case. Now, a curve like this tells a story for a business stakeholder and for the organization to make business decisions. For example, you could say, hey, well, based on this projection, I'm totally going to stop at 24%, and that's where I'm going to maximize profit. So I'll just only market to the top 24%, and then I'll get $350,000 profit from this marketing campaign. That's what the expected profit would be. That's a totally reasonable choice, but it's not the only choice. You could also, depending on context and business philosophy and priorities, a stakeholder might say, hey, no, let's stop at 74%. That's where we break even. So we could essentially market for free. If we're less concerned about immediate term profits, we could market for free to 74% of the customers, arguably a lot better than marketing to 100% of them at a cost of $550,000. Either way, if you draw the line, that's how you're deciding to use the model. So the model doesn't dictate exactly how it's to be used. You have to decide where to draw that line. Let's say we did draw the line at the 24% mark. What that means is that we've used the model to make whatever it is, 100,000 yes-no decisions. We've decided the top 24% all belong in the yes bucket and the rest are in the no bucket. That means I save 76% of my marketing costs. I cut the cost of the campaign by that much, which is huge. Now, I forsake all those potential responses from those further down the list, depending on the context of the campaign, if people only buy if contacted. But since most are concentrated in the top, it's a well worthwhile trade-off from the standpoint of immediate term profits. So this is what it means to decide how to use a model and its probabilities to drive that many yes-no decisions for each individual prospect. Okay, so we already sort of got into metrics, but let's take a step back. It turns out that most metrics focus on technical metrics, including precision, recall, and accuracy. And that's the one you hear about all the time. Accuracy is usually impertinent and misleading, and I call this the accuracy fallacy. Here are 4 real headlines. AI can tell if you're gay. Artificial intelligence predicts sexuality from one photo with startling accuracy. Linguistic analysis can accurately predict psychosis. AI-powered scans can identify people at risk of a fatal heart attack almost a decade in advance. This scary AI has learned how to pick out criminals by their faces. So here's the deal with the accuracy fallacy. These headlines are essentially lies. They convey misinformation, which is as follows. Most people reading these articles, even technical data scientists who don't delve into the details of the actual research study, are given the impression, because it's tacitly conveyed with this language, that the model is capable of differentiating between positive and negative cases and overwhelmingly being correct for both positive cases and also overwhelmingly being correct for negative cases. But no, we don't have clairvoyance. We can't expect computers to, whether a human's going to click, buy, lie, or die. What we can get is predicting better than guessing. But we can't get highly confident predictions either way in the vast majority of cases. That would be a magic crystal ball. Unfortunately, we don't have one of those. So let's dive into that in a little more detail to give you a sense of why that's misleading, what's going on here. In the case of predicting sexual orientation, that comes from a Stanford study. And in their data, in their sample, gay individuals were the minority category, and everybody knows that. The majority is heterosexual, 7%. which means that if a model just always predicted everybody as heterosexual, it would never correctly identify any of the minority cases, which is gay in this case, but it would have 93% accuracy, because all accuracy means is how often are you correct. So a really dumb model that just always says heterosexual would be 93% accuracy. What they actually said in their headline, and by the way, it made it, for example, to the front page of The Economist, is a 91% accuracy that's not as good. Unfortunately, they're misusing, and that's part of the problem, they're misusing the word accuracy. They actually mean something called AUC, area under the receiver operating characteristic curve, which is kind of has a narrative that sounds like accuracy, but it's something else entirely. But the bigger point is that, look, it's not a crystal ball. In fact, let's look at that concretely. If you use their model, now it does predict better than guessing, right? And that's generally helpful to know. It doesn't necessarily tell you the business value, but that's a start. It's not, that doesn't mean it's highly confident for most cases. So if you use their model and you drew a threshold so that it would correctly identify 2/3 of gay individuals, which is possible, that in and of itself is not good, because it turns out in that case, it would, more than half the time it actually labels somebody or predicts somebody as gay, it would be wrong, a false positive. We generally use the word positive for the minority case, whatever of the two categories happens less often. If you wanted to identify even more than 2/3 of that minority category, it would have false positive rate even higher, right? So this is perpetrated by the media with headlines and articles that are using the phrase high accuracy and conveying that it has that kind of crystal ball, high confidence for both positive and negative cases. Totally impossible, implausible for so many things. Spotting cyber bullies, predicting heart attacks. There's a million examples. If you want to read more, read The Accuracy Fallacy, which is an article I published in Scientific American blog. Or there's the metrics chapter of my new book, The AI Playbook, kicks off with this topic. So taking a step back, basically there's kind of two kinds of metrics, and it's really important to know the difference and to use both of them. Most projects only use technical metrics such as precision recall, AUC, and accuracy counts as well. And these only tell you the pure predictive performance. That is to say, they tell you only the relative performance in comparison to a baseline like random guessing. That's not useless. It's helpful to know, hey, it predicts better than guessing. And indeed, you can't expect it to be magical. And to know that it predicts better than guessing is a good sign. But ultimately, what you care about are business metrics, key performance indicators, profit, ROI, savings, number of customers acquired or saved. Concrete, this is the lingua franca of business. This is what your stakeholder or client would expect if you're a data scientist. And if we're not, these two columns are so distinct, they don't directly map. One does not directly tell you the other. You have to measure or estimate them separately. It's just arithmetic both ways. We're not doing the rocket science here. All we're doing is measuring how good the rocket science is, how well the model predicts, and how much business value it could deliver. But we have to do the calculations. So that disconnect is absolutely key. It's the topic of my new MIT Sloan Management Review article, which you can find online, What Leaders Should Know About Measuring AI Project Value. Totally, it's about, look, we're doing technical metrics. This is the definition of business metrics, why there's a difference, why we need to use both and not just the technical ones. Also the topic of the metrics chapter, which is chapter 3 of the new book, The AI Playbook. And I should also mention that I've co-founded a startup called Gooder AI at gooder.ai, which does that, which actually calculates the business metrics. This is the last remaining technical component missing to help improve the last main missing component that's really contributing to that high failure rate of enterprise machine learning projects. If you're interested in learning more and would like to be considered as a beta customer for our solution to calculate business metrics, go to Gooder AI and send us a message. So let me give you one concrete value. I'm going to give you a little tour of the arithmetic so you can just get a sense that, hey, this isn't rocket science. It's not a big deal, and it's absolutely necessary. to convert from technical to business metrics. And to that end, let's look at fraud detection, where what's predicted is whether a transaction is fraudulent, whether it's legitimate, whether it should be authorized. And what's done about it? Well, if it's high risk of being fraudulent, then either hold or audit it, right? In the case of payment cards, it's automatically held instantaneously on the fly. So what we're trying to do is strike the right balance with this thing. It's not a magic crystal ball. It predicts better than guessing. It's still going to make errors, and there's two different kinds of errors: false positive and false negative. So false positive, false flag, is where you've inconvenienced the card holder, right? You said, hey, this is fraudulent. Let's disallow the transaction for the moment. Let's hold it. And now in that particular scenario, that error, the legitimate customer is inconvenienced. That costs the bank something, perhaps on average $100, since customers, at least over multiple experiences, will start using a different card instead in their wallet. Whereas the other kind of error is probably worse, and that's where you don't detect fraud, where it's a false negative. You say this is not, the model says this is not fraud, but it actually was, so it allows a fraudulent charge to go through. The criminal gets away with the loot, and the bank has to eat the cost, which could be on average about $500. So the value of a better predictive model is that it allows for better trade-offs. It's up to the bank, the organization, to decide how to navigate those trade-offs, but at least you're offered those by the power of prediction. So let's say a medium-sized regional bank that's issued 100,000 cards, and the fraud rate is 1 out of 1,000, 0.1%. Well, if you do a little arithmetic, that could be costing the bank $50 million a year in fraud losses if they had no fraud detection. Right? So now I'm just going through this arithmetic super fast just to give you a sense that there's no calculus. It's just some arithmetic. You can take your time. I'll give you a link so that you can go try it out yourself. A little more complex arithmetic. If I were to step through this, I don't want to bore you, but just again give you a sense. If we have a predictive model, how much better would we do by sometimes blocking transactions that are relatively likely to be fraud? So if we tune the model, it's not perfect, and in fact, when it blocks transactions, it's still probably not fraud, but much more likely to be fraud than average. Maybe about 40%. Well, if you do that, then you're striking a much better balance. You are causing these inconveniences, but enough of the times you're actually correctly capturing fraud, preventing those more costly errors. And the bottom line is that you end up with an aggregate cost across those two different errors of $34 million. That's a $16 million savings with a fraud model compared to without one. And you're fighting crime, right? You're preventing fraud. You're improving the integrity of a primary system of commerce, right? So this is good, right? So my point again is, and this is the same math. You can maybe jot this down quickly if you want to go try it out yourself with this spreadsheet. It's the same math. The same math is in the Sloan Management Review. There's a sidebar at the end that you can pop open, the Sloan Management Review article I mentioned. Same example is also covered in Chapter 3 of my book. Just to get some concrete arithmetic, again, it's not the rocket science. It's how good is the rocket science, how well does it perform, and how do you translate that into potential bottom line wins in terms of profit. Okay, let's go to some of the other aspects. I mentioned you have to understand three things that are semi-technical when you're involved with these projects: what's predicted, how well, and what's done about it. The first of these three is what's predicted, and you have to define that very carefully. I've made it clear that these things deliver probabilities, but probabilities of what exactly? You have to decide that very carefully, because that relates to how you're going to use those probabilities. So for example, in this, I gave this use case of targeting marketing, and what you're predicting is, will the customer buy if contacted? But no, you actually need to get a bunch more specific than that. But it's not really technical, it's just detailed. So for example, you might come up with something like, well, we want to predict which customers, if sent a brochure, will the customer buy within a time. You have to set the time window. You can't wait forever to find out what the outcome was. 13 days with a purchase that it qualifies, right? It's got to be at least $125 after shipping, and not return the product for a refund within 45 days. So it's a legitimate purchase. We made a profit, right? Something along those lines. the caveats and qualifiers that are pragmatic and practical from a business standpoint. They're not going to be determined by data scientists operating in a vacuum. These depend on business input. There could easily be 3 times as many as in this example. So it's sort of a long run-on yes-no question, right? But you need to work out these details, and this is one of the places where you need this tight, detailed collaboration, deep collaboration between the business stakeholders and the data scientists in order to get it right so that you're actually driving this project towards success. Okay, so we've kind of talked about these 3 main things so far. The 3 semi-technical concepts that you need to understand in general and get involved in the details of for any particular machine learning project. What's predicted, how well, and what's done about it. And those correspond to the first 3 of the BizML enterprise practice for running machine learning projects that I present in my book, The AI Playbook, just in a different order. So these first 3 of 6 steps are basically the pre-production steps where you're collaborating between data scientists and business stakeholders to sort of establish exactly how this project's going to use machine learning, what's going to be predicted, and what's going to be done about it. So let me just step through. First, establish the deployment goal. So the deployment goal, the use case, the project is defined by the first and third, those 2 things. What's predicted, what's done about it. Predict fraud to block transactions. Predict which satellite's going to run out of battery to inspect that satellite, which costs something. It's all about allocating resources, right? Limited resources and money. The second of these, establish the prediction goal. Well, there's where you get more detailed in the first of that pair. So what's predicted, what's done about it. Now in step 2, the prediction goal, we're going to go into what's predicted, but get a lot more detailed along the lines of what I did a minute ago. Really fully fleshing out what data scientists know as the dependent variable, the target, the thing that the model's meant to actually predict. And then finally, establish the metrics, right? So as we've discussed, there's a bunch of technical metrics. There's a bunch of business metrics. We need to decide which ones are pertinent and what the standards should be before we can authorize deployment for both technical and business metrics. And then the other 3 steps are basically the same production technical steps for any machine learning project. All data scientists agree on this. You have to prepare the data, train the model over that data. That's the number crunching that learns from that data and generates that golden egg model. And then use the model, number 6, the culminating step. Deploy the model, get it into operations, start using it to make predictions, and then act on those predictions so that operations improve, which requires that they change. So that's where you're actually integrating it. So essentially, step 1 is to plan for step 6. This is reverse planning. Now, that last step, the culminating steps, that's where you're actually changing existing business operations, which means you need change management. It seems kind of obvious, but it's got to be said. Change management is a well-understood discipline, and everyone knows it's hard. The problem with machine learning is that people don't conceive of it as change management. They think this is the best of technology, it's intrinsically valuable, and they conceive of it as a technical or quantitative number crunching project, underestimating the amount of change management and planning that's going to need to go into it. So that is to say, if you're doing a machine learning project, do change management. Don't just think of it as a technical project. Let's remember that. But the overwhelming focus today is not on that last step. Ironically, it's on the number crunching. We fetishize it. It's the best of science. It's so cool, learning from data to predict, ascertaining and finding formulas and patterns from historical data that then pan out over new unseen cases. That's great. I love it. It's the reason I got into it, and probably most data scientists got into it in the first place. But it's not valuable unless you act on it. This is sort of the syndrome, is that new data scientists, burgeoning data scientists and new students, they just flock to the hands-on, and educators and technical books all enable it. The first step is almost always open the machine learning software tool on your screen, load the data, and then train the model. But that bypasses those first 3 production steps. Only by fully fleshing out the business goal, what the fully detailed prediction goal needs to be from that, And that, in fact, that's what defines the data prep. The way you manifest in the technically what you're trying to predict once you've defined that prediction goal is by how you prep the data, not in how you operate the machine learning. It's actually the data prep where you're manifesting that. The data is not going to prep itself. The data exists at your organization in whatever form and format that it happened to have been accrued in across database tables and systems and silos. That data prep is a really, really big, often overestimated technical step. So you're stepping past a bunch of technical and business pre-production steps. This is a syndrome. This is a problem, right? So we've got data scientists, and they, as I mentioned earlier, both sides are kind of pointing the finger at the other for the responsibility to get this last piece in place. Data scientists will say, look, I'm technical. My job's just to make a model. Those are management issues. It's outside of my purview. And the value of the model is a no-brainer. It's self-evident, and of course the organization is going to use it. That's not up to me. So that's not my problem. Whereas on the other side, the business professional is saying, what's predicted, how well, what's done about it? That level of detail involved with any kind of details related to the data science or machine learning project. That's why I have data scientists. I delegate all that technical stuff to them. This is why the hose and the faucet fail to connect, right? These two sides need to unify. They need to bridge a chasm and come together and agree on this business practice that's driven by semi-technical joint understanding and collaboration. It's so ironic because we're focused so much on that core technology, the sort of rocket science. It's sort of like being more excited about the rocket science than the actual launch of the rocket. But obviously what you see on TV a lot more is the launch rather than a rocket science just sitting in the lab. And the rocket science is cool, but there comes a point where you say the rocket science isn't enough. Let's actually get this rocket launched, right? Isn't that probably a pretty good idea? The business professional has puts another hand up or a wall up and says, look, I don't need to look under the hood of my car to drive a car, which is true. I personally don't know where the spark plugs are in my car, and I've looked under the hood maybe once. And when I did, I was like, wow, look, there's so many parts. I'm totally clueless. But to drive a car, I have a lot of expertise. I know about momentum and friction, the feel of the car. I know how the car operates. I know the rules of the road, and I know mutual expectations of drivers. Analogously, you need the same kind of semi-technical expertise to drive a machine learning project to successful operationalization. Now, I've given you a sense of that, what's predicted, how well, and what's done about it with some examples. But I can't give you all that semi-technical knowledge in a short presentation. On the other hand, it's not the rocket science part. It's how to capitalize, how to use the rocket science. And it's cool. It's interesting. It's much more accessible, easy, practical, and relevant than high school algebra. Everyone needs to and should learn it. This is the new data literacy. So no, it's not a half-hour talk, but it's just a book. And that's why I wrote this book, the AI Playbook. So to wrap up, we need to reframe machine learning projects. Right now, they're defined and considered almost entirely only with regard to that technical scope. The technical practice of prepping the data, train the model, deploy it, the core rocket science part. But there's this whole other side, the business side of machine learning projects that are generally being neglected, which is leading to this failure, right? We need a standardized paradigm or playbook that I call BizML. We need stakeholders who've ramped up on semi-technical understanding to deeply collaborate end-to-end across the life cycle, across that practice, the project steps. Between data scientists and business side, that deep collaboration, that's the requirement. Now, these aren't two sort of separate sides. This is a business project with a technical component. In fact, we should probably rename machine learning projects to be operations improvement projects that use machine learning as a critical, necessary technical component. So these are my conclusions. gain a semi-technical understanding of machine learning. This is the new data literacy. And then once you've ramped up on that, you're now in a position to participate. More than anything, enterprise machine learning projects need you, if you're a business side stakeholder, once you've ramped up, more than better technology, more data scientists. This is the main missing thing, is that collaboration with you as an well-informed, participating, deeply collaborating business side stakeholder. Now, end to end, let's agree on the steps. I formulated as BizML 6 steps. Here are the 6 steps again.